Okay, welcome to class today. Those of you that come here during the Monday of an exam week are the true diehards, so I appreciate that. So as you can tell, the crowd is small today, and because of that, the plan for today is we're not going to probably go as long as we normally do, because we don't need 2 full lectures to cover what we wanted to do this week, so hopefully no one's too upset if we get out a little bit earlier than we normally do. So we have an announcement that was one of your fellow students was asked me to present, and that's about a comedy show tonight, which starts right after class at 6 p.m. So if my jokes aren't doing it for you, you can go see some real comedians tonight in the Student Center at 6 p.m. So, all right, so that's what we wanted to talk about. And then some other announcements that are right here that are related to the class. I think all of these I've mentioned before, so there shouldn't be any surprises, but just to give continual reminders about all the extra stuff we have going on during the last 2 weeks. So obviously, as you all know, this week is the third midterm exam, the last of the 3 midterms, which is going on right now and will continue through Wednesday. And then to get ready for the final exam, which we have a quick turnaround that comes right next week already, we'll have the first part of our final exam review session is going to be this Friday. So it's going to be sort of during the normal exam review time slot. That's the 27th, I believe. Yeah. And it'll be in this classroom as we normally do. So I believe the way I have it broken down, if you're going to follow along with the review questions, which are now posted in Blackboard, this Friday we'll plan to do questions 1 through 20 in the review, so the normal 20 questions that we would cover in an exam review. And then next Monday, in the very last day of class, we will go over the remaining exam review questions for the final exam. So the last day of class won't be anything new. It'll just be review for the final, and we'll plan to cover the last 14 questions that day, which is I think, pretty conservative set of questions to cover in a normal class period, so I won't have to keep you late or anything on the last day. All right, so that's what's going on, and then obviously, as I mentioned a few times already, because a lot of you like to come see me during the last 2 weeks to talk about exam preparation or grades once that becomes more apparent, I have my office hours for the next 2 weeks posted in Blackboard, so there's no confusion or mystery about when I will and will not be there. So any changes I'll have to make, but I don't anticipate any. All right, what we're going to talk about today is we've spent a few times now talking about the structures of solid state compounds. We talked about the structures of metals last Monday, which is the last topic that'll be covered on the current exam, and then on Wednesday we covered the structures of ionic compounds, which are closely related in some ways. And now we're going to move away from solids again and start talking about some properties of liquids, specifically what's called vapor pressure. So that's the major topic today. We'll see a couple other things towards the end as well, dealing with phase changes, which is the last major topic in this course. All right, so let's talk about what vapor pressure refers to. So we already discussed and defined a little bit of what vaporization itself is. So vaporization is the process of converting a liquid into a gas. So far what we've covered in chapters 8 and up until 9 and up until now in chapter 9 is single phases. So we've talked about properties of gases in chapter 8. We've talked about properties of liquids at the beginning of this chapter, properties and structures of solids. Now we're going to start talking about changes in phase between 2 or more of these. So between solids and liquids, or liquids and gases, or even solids and gases, we're going to talk about these different phase changes. And the first one we're going to talk about is vaporization, which is the process of converting a liquid into a gas. And so the enthalpy of vaporization is abbreviated as delta H VAP for delta H of vaporization. And just like any enthalpy change, it's associated with 1 mole of substance. So we should recognize that we have to put heat into a substance to get it to convert from a liquid to a gas. We have to break intermolecular forces of attraction. And so the enthalpy change that's associated with this is what was referred to as the enthalpy of vaporization. And specifically, as I said, is for 1 mole of substance. And we're always, as I said, breaking intermolecular forces of attraction between the molecules. When we do this, we always have to put heat into the system to cause this phase change from liquid to gas. And that means the sign for the vaporization enthalpy will always be positive. So it's always an endothermic process to vaporize something, meaning that the sign of this delta H value is going to be plus, greater than 0. And then we should also be familiar with the reverse process. So we defined this early on, condensation, which is just the opposite. So condensation is the process of going from gas to liquid. Which we see all the time here in Houston as water vapor from the atmosphere condenses onto cooler surfaces like windows, for example. So condensation is the reverse process. Molecules in the gas phase become liquid. And then thinking of the properties of delta H that we learned a while back, if we're going to define a delta H for condensation, an enthalpy change associated with condensing gas to liquid, since this is the exact opposite process as vaporization, the delta H for this is the same in magnitude but opposite in sign. So the delta H for condensation is just the negative of the vaporization enthalpy, which of course means that this would have an exothermic or negative delta H associated with it. So these are the two processes, and those are the associated enthalpy changes, and we're going to talk in more detail about those a little bit later today. But what we want to get into at the beginning now is what's referred to as vapor pressure. So we introduced, really out of necessity in Chapter 8, the concept of vapor pressure, which is the idea that when you collect a sample of gas over water, you have some small pressure that's contributed from the water itself. And so vapor pressure is when you have a liquid in a container, some portion of those molecules at the surface of the liquid are going to escape into the gas phase, and that's going to give you then a little bit of vapor pressure, a little bit of that gas phase molecules that are going to exert a pressure. So let's talk about then what causes this vapor pressure, the idea that if we start with a liquid, we're going to get some portion of molecules in the gas phase. So if we imagine we place a liquid into a closed container, so at the very beginning, when we do this, there's going to be net vaporization as surface molecules escape into the gas phase. All right, so at the very beginning, as I said, we have, I'll draw that here on the left. We have our liquid sample, and some molecules at the surface are going to vaporize, are going to go into the gas phase. So initially, as I said, there's net vaporization. But then, eventually, a constant is established because later on, we get to what's called an equilibrium, which you'll talk more about in Chem 2, should you have the pleasure of taking that course as well. And when we get to this equilibrium, what's happening is that we always have molecules leaving the surface, but we have basically the same number of molecules that are going to, at the same rate, condensing back onto the surface. So you have sort of this dynamic situation where there's always molecules leaving the surface, there's always molecules then condensing from the vapor phase back into the liquid phase, and in that you have no change then in the number of molecules that are in the headspace or the gas phase. So there's going to still be some molecules up here in the gas phase that are zooming around causing this small vapor pressure, but in that you're not going to be increasing the number of gas molecules that are in there, so you're going to get to a constant steady pressure. So eventually a constant vapor pressure is established as everything gets to an equilibrium. All right, so if we talk about then this in sort of a graphical representation, we're going to indicate the rate of two processes as a function of time. So this is how fast these two different processes are happening. So as I said, we have vaporization occurring in this sample, which is molecules going from the liquid to the gas phase. And the vaporization rate is constant. it's a function of temperature, which we won't really talk about the exact functional form of this, but at a given temperature, the vaporization rate for a liquid is constant, which means that over time, the vaporization rate, which I'm showing in blue, is going to be ideally a straight line, which I can never draw the first try. That's straight enough. So the vaporization rate is going to be constant over time, meaning that the rate at which molecules go from the liquid to the gas phase doesn't change. But as we get more and more molecules into the gas phase, there's going to be more of them that are available to then condense back into the liquid phase. So as we start building up molecules in the gas phase, our condensation rate, which I'll show in red, is going to then increase. And it gets to eventually to a steady value. So what happens then is, at the very beginning, when we first introduce the liquid, there are no molecules in the gas phase, so there's no way for those molecules to condense back into liquid because there aren't any. But then as more molecules get into the gas phase, the rate of condensation increases, and eventually they're going to equal each other. So once you get to this situation where the two rates, the rate of condensation and the rate of vaporization, equal each other, that's when you get to a steady, constant vapor pressure. You're not going to be then changing the vapor pressure anymore. And so that's why the vapor pressure doesn't just continually increase. If you have a closed container, you're going to have some vaporization, but eventually that vaporization is going to be equalized by molecules that are condensing back into it, and you're going to get to a constant pressure. You're not going to just have more and more molecules that escape into the gas phase and build up the pressure more and more. So that's kind of a molecular picture of what causes vapor pressure. It's molecules at the surface going into the gas phase, which then is eventually equalized by molecules recondensing. The next thing we'll talk about is how we measure vapor pressure. And so the way we can do this experimentally is with a barometer. So the first thing we're going to do is we're going to measure the atmospheric pressure using a barometer. So drawing a quick crude picture of a barometer. Again, a barometer is a plate of mercury, an open plate of mercury or bowl of mercury. And then you have a glass tube that's inverted in there. So you have a closed glass tube that's inverted in your tube in your dish of mercury. And so what happens, as we talked about back in chapter 8, is that atmospheric pressure pushes down on the liquid and it forces some of it up into the tube. And then by measuring the height that this is above the surface of the liquid, that gives you the atmospheric pressure, which in normal conditions is around 760 millimeters of mercury. So that's what we do first. We measure the atmospheric pressure. And initially, when you have a barometer, this part of the tube up here is just vacuum. So there's nothing in the tube initially in that part of it. So you just have, basically it's the weight of the mercury opposing the atmospheric pressure that gives you this height difference. But then what we want to do if we want to measure the vapor pressure of a liquid is we inject a liquid into the top part of the barometer. So we need to have some way of doing that, of course, and not just regular barometer. But if we can inject a liquid into the top part of the barometer, we get a situation that looks like this. So we're going to still have our same barometer. With the same tube. So we still have the same atmospheric pressure pushing down this way and forcing mercury up the column. However, what we now have in the headspace of our column is we have some vapor pressure that's going to be opposing that. So whatever liquid we inject into the top part here is going to have a vapor pressure that pushes down on the column, and we're going to get a different height then. So we're going to have then some new value for our barometric pressure H, because it's now opposed by a vapor pressure that's pushing down. So the vapor is inside of there, pushing down on the column and opposing the atmospheric pressure. So you have this sort of competition between atmospheric pressure and vapor pressure. So as an example, if we assume we have exactly 760 millimeter atmospheric pressure, So let's say we're right at normal sea level conditions. So if that's our atmospheric pressure, this height that we measure now in the presence of a vapor is going to be the difference between atmospheric pressure and the vapor pressure. So if we put water into the headspace of our barometer, into the top part of our barometer, at 25 degrees Celsius, the height that we would measure, this h here, is going to be instead 736, so it's going to change by some small amount, which means then that the vapor pressure of water at this temperature is 760 millimeters of mercury minus 736, which is that new height, which gives us 24 millimeters of mercury. So we've seen a lot of homework and now test questions in Chapter 8 towards the end where we said, the vapor pressure of water at 25 degrees Celsius is 24 millimeters of mercury. We give you that number and you'd have to know how to use it to solve those types of problems. Here's how you would measure it. So that's where that number comes from. We don't just pull it out of thin air. We actually can measure it using a simple barometer like this. And this just gives you then an idea of how we go about this measurement. But the more important things to think about today are the properties of vapor pressure and the different factors that influence what the value of the vapor pressure is going to be. So, here we say, just with this random example, the vapor pressure of water at 25 degrees Celsius is 24 millimeters of mercury. But what happens if we change the temperature, or what happens if we talk about a substance other than water? How does the vapor pressure compare in those situations? That's what we're going to deal with a lot today. So the first thing we'll talk about is the temperature dependence of vapor pressure. So as we talked about with gases, when you have a sample of gas molecules, and the same thing holds true for liquid, they have a distribution of kinetic energies or distribution of molecular speeds. They're not all at the exact same kinetic energy or same speed. They all have a distribution and some average value that we can determine. So the same thing happens in liquids. We can draw sort of one of these plots. That's the fraction of molecules that have a given kinetic energy. So let's say we compare two different temperatures. Let's do T1 here, which is a lower, colder temperature. And let's say we have a distribution that looks like this. So it's a normal distribution, some average value. And then the reason that we have vapor pressure is that in this sample of liquid, there's going to be some small fraction of the liquid molecules that have enough kinetic energy to escape the surface. So we have this, this property called surface tension. We have these intermolecular forces that are sort of holding the molecules in the liquid phase. But some small percentage of the molecules here, let's say at some arbitrary point here, are going to have enough kinetic energy to escape. And that's what gives rise to vapor pressure. So at this first temperature, which I'm calling the lower temperature, or T1, some percentage of the molecules have enough kinetic energy, they escape into the gas phase, and they give rise to that vapor pressure that we've been talking about. Now let's look at what happens if we raise the temperature to a higher temperature, which I'll show in red, because red means hot and blue means cold, as we all know. Alright, so let's look at the distribution, how that changes when we have a higher temperature. So as we talked about for gases, when you increase the temperature of a gas, the distribution gets wider and the average shift towards higher values. So just like in a gas sample and in a sample of liquid, the average kinetic energy increases when you increase the temperature. And so our new distribution will look something like this, where it's a broader distribution and the average is shifted further to the right at a higher kinetic energy. And so what that means now is that if this is the kinetic energy value that's required to escape the surface, we now have a much larger fraction of our molecules that have enough kinetic energy to escape the surface. So we have more molecules with high enough kinetic energy to escape. And so then what that means is that if we have more molecules escaping the surface at the higher temperature, the vapor pressure will increase as we raise the temperature. Alright, so the conclusion of all of this, and the most important thing to know for now, is that vapor pressure increases as temperature increases. And again, the simple reason for that is when you increase the temperature, on average, the molecules have higher kinetic energy, and then more molecules have enough kinetic energy to be able to escape from the surface of the liquid, enter the gas phase, and then contribute to that vapor pressure. And the more molecules you have in the gas phase, the higher the vapor pressure will be, as we know from ideal gas equations. The more molecules or the more moles of gas you have, the higher the pressure will be. All right, so that's how vapor pressure works. That's kind of the physical origin then of the temperature dependence. So now let's talk about then the equation that relates vapor pressure to temperature. So we're not going to derive this one. It comes from a branch of chemistry called statistical mechanics, which is exceedingly complicated. So we're just going to give it to you. And the equation that comes out of this is that the natural log of the vapor pressure. So if you don't know how to use the natural log key on your calculator, now's the time to learn, because it's going to come up in this part of the course for the first time, and it'll come up a lot in chemistry too as well. So anyway, the natural log of the vapor pressure is equal to the negative of the vaporization enthalpy divided by the universal gas constant R times 1 over temperature plus some constant C. Now the nature of this constant depends on the type of substance that we're talking about. So it's different for every substance out there. And so since we don't want to necessarily have to learn or use this constant for every single substance in the world that we're trying to calculate vapor pressure for, the more useful form of this equation is to instead compare the vapor pressure at two different temperatures. So we're going to compare two different vapor pressures at two different temperatures, and we're going to use a comparison to actually derive an equation that's in terms of both of those. So it's going to look like this. The natural log of the ratio of two vapor pressures, P1 over P2, is equal to the enthalpy of vaporization divided by R. Now there's two forms of this equation that you'll see depending on which resource you look at. I think the way I did it is exactly the same as our textbook, which has them in this order. So where T2 and T1 are, the T2 is the temperature at which you're measuring the second vapor pressure, P2. T1 is the temperature at which you're measuring the first vapor pressure, P1. And they're written in this order. Now, some cases you'll see a negative sign out front of this equation here, and then these two terms will be flipped. It's mathematically equivalent, but there's just two ways of writing it, one with and without a negative sign. Or you could flip this side of the equation, make it P2 over P1. So there's a lot of different ways of writing the same equation that are mathematically equivalent. This is the way that I'll use it, and the way I think that your book has it, but if you've learned it a different way in the past, they're all same mathematically. So a couple of things to keep in mind when we're using this equation is that the temperature has to still be in Kelvin. That hasn't changed from what we've been doing. And then we're going to use the value of R, that's the second value, the one that we don't use as often so far, which is 8.314 joules per mole Kelvin. The reason being that our enthalpy of vaporization is going to be in terms of joules, so we want R to be in joules when we divide the two in this factor that goes out front of the temperature terms. So we want to make sure we use the correct value of R when we do this, and make sure that our delta H vaporization is in joules. And then what this equation allows us to do is we can look at sort of the behavior of different substances where we're plotting their vapor pressure as a function of 1 over the temperature. So in this equation here, if we use this form of the equation that I gave up top here, we can plot on the y-axis, we can plot the natural log of the vapor pressure. On the x-axis, we can plot 1 over the temperature. And that means from this equation, if this is y, and this is x, and this is our intercept b, the slope of this is going to be given by negative delta H over R. And then the intercept of that plot would give us that ill-defined constant C that we're not going to really worry about too much, but you'd be able to determine. So the point being that if you do a plot where you measure the vapor pressure of a substance at a bunch of different temperatures, and then you plot that vapor pressure, the natural log of that versus 1 over temperature, that slope will give you then what the vaporization enthalpy is for that substance, and that's a common way then to do that. So if we compare two different substances, let's do water first. Let's say water has a plot that looks like this. And so again, the slope of this plot, it's always going to be negative because it's negative delta H over R, where this is the vaporization enthalpy. Vaporization enthalpies are always positive, so that means the slope in these plots would always be negative. So you're putting a minus sign out front. And then the other thing we can do also is if we look at a different substance, let's do one like diethyl ether, for example. I'm just doing this qualitatively. So diethyl ether is another liquid that has this formula here. Not that you just have to know this now. So in diethyl ether, we don't have the difference between water and diethyl ether is water has, as we know, two OH bonds, meaning it has hydrogen bonding interactions that are prevalent. Diethyl ether is still a polar molecule, but it doesn't have any hydrogen bonding interactions because there's no hydrogens bonded directly to the oxygen. So if we look at the slope for diethyl ether, it's going to be a lot smaller, which ideally is a straight line. It always takes me 2 tries, as you guys know. There we go. So diethyl ether would have, that's too flat. I'm too picky. There, that's better. So if we do a different substance like diethyl ether, we would find a different slope that tells us that this has a different enthalpy of vaporization. So every substance is going to have a characteristic slope when we make a plot like this, where that slope is given by delta H over R, or negative delta H over R specifically, which then we can then back out the vaporization enthalpy if we wanted to. So that's kind of the usefulness of this equation and this relationship. Let's do a couple of example problems of how we use this equation then, and things that you might see then on homework assignments and tests that are coming up. So let's talk about that substance diethyl ether that has a vaporization enthalpy of 29.1 kilojoules per mole, and it has a vapor pressure of 0.703 atmospheres at 25 degrees Celsius. What is this vapor pressure at 95 degrees Celsius? So again, this problem here, we're just going to set up that equation that we learned, which relates to vapor pressures and two temperatures, and we're going to solve for the vapor pressure at the other temperature. Okay, so it's going to be this form that I've used, that I gave in the previous slide. And then in this problem, we just have to figure out what's the given information and what it is that we don't have. So our initial temperature that we're told is 25 Celsius. These have to still be in Kelvin, so it's going to be 298 Kelvin for T1. That's 25 degrees Celsius. The second temperature that we're comparing it to is 95 degrees Celsius. If we convert that to Kelvin, we add 273 and we get 368. So these are the two temperatures we're comparing. We can think about this a little bit before we even start the math, as I like to do. So, what happened to the? It's not supposed to. Oh, jeez. All right, it's back. Sometimes it just does whatever it wants. All right, so that's going to be our second temperature. That's our first temperature there, 25 and 95. We're told that the vapor pressure at 298 Kelvin. So we're going to label that as P1. Again, in these problems, P1 and P2, T1 and T2, those designations are arbitrary. We have to make sure that P1 matches with T1 and P2 matches with T2 when you put them in. So if we're calling T1 298 Kelvin, P1 would be the vapor pressure at that temperature, which we're told is 0.073. And since we're comparing that to a higher temperature, the vapor pressure that we're going to determine in this should be higher than 0.703 atmospheres. If you increase the temperature, you should get a larger vapor pressure out of this. All right, so then let's set up the equation with the numbers that we have. The natural log of P1 is 0.703 atmospheres, divided by P2, which is our unknown in this case, is equal to vaporization enthalpy over R. So we're told that the vaporization enthalpy is 29.1 kilojoules, but again, let's think about units for a second. We're using the value of R, which is 8.314 joules per kmol, which means our vaporization enthalpy has to be also in joules. So it's 29.1 kilojoules per mole. To use it in this equation, we have to convert that to joules, which is 21.9 29,100 joules per mole. All right, so our delta H has to be in joules so that it divides out correctly with the value of R that we're going to use. And again, this second value of R that we're using is still on the periodic table, so you don't have to memorize it. But you do have to remember to convert to joules when you have vaporization of the P's, which are usually in kilojoules more often than not. And then we put in the two temperatures. So again, in this form of the equation, it's 1 over T2 minus 1 over T1. T2 is the second or highest temperature, 368. And then T1 is the first temperature, 298. All right, so algebraically, this becomes a little bit trickier. And so what we find then is, if we work out this numerically, we have the natural log of 0.703 over P2. Since we haven't done this algebra before, I just want to make sure we're clear on the algebra part of it. So when we multiply out this side of the equation, these are all numbers now, so we just divide 29,100 by R, multiply by this difference in temperature terms. What we get on that side of the equation is a negative number. I got minus 2.234. And then if we want to undo a natural log, remember from your previous math classes that you've taken or are currently taking, we just have to take the exponent of both sides. So if we do the exponent of both sides, that gets rid of the natural log on this side. So 0.703, come on back. 0.703 divided by P2 is equal to e raised to the minus 2.234 power. So when we want to get rid of natural logs, we use e. Euler's number, I think is what it's called. Which that comes out to 0.107. So now it's a simpler problem. You just solve for P2 by cross-multiplying and dividing. And we should get that P2 then is equal to 6.56 atmospheres. All right, so the required algebra on this for this equation steps it up a notch from what we've seen before, but I don't think it's too difficult. And again, just get used to using natural logs and exponents on your calculator, since we haven't had to do that yet in this course. All right, so we get a vapor pressure of 6.56 atmospheres. Expectedly, that's higher than the initial vapor pressure because the temperature is higher, and we see that at that temperature it's quite a bit higher than even atmospheric pressure. All right, so that's how we deal with that equation. Any questions on that, by the way, before I move on? All right, so the next thing we'll see then, we talk about the relationship now between temperature and vapor pressure. I don't know why there's this random circle here. Let's talk then about the relationship between intermolecular forces and vapor pressure, which we're going to compare at a more qualitative or relative level. And so what we should think about is, again, the implication. Let's say we have, oh no, I dropped my stylus, but luckily it's easy to push out. I thought I was done. So anyway, the relationship between intermolecular forces and vapor pressure. So if we have stronger intermolecular forces, we would imagine that means that it's harder for the molecules to leave the surface of the liquid. They're held more strongly to the surface, so that would suggest then that we would have a lower vapor pressure. So there's sort of an inverse relationship between the strength of the intermolecular forces and the observed vapor pressure. Okay, stronger intermolecular forces implies a smaller or lower vapor pressure. And that's because, as I said, vapor pressure requires molecules to escape the surface, and if the IMFs are stronger, it's harder for them to do that. All right? And then if we talk about the relationship between intermolecular forces and enthalpy of vaporization, which is another way of thinking about the same concept, stronger intermolecular forces means we're going to have to put more energy into the system to vaporize the vaporize liquid molecules into the gas phase, which suggests then that stronger intermolecular forces correlate with a larger enthalpy of vaporization. All right, so we talked about all these different properties that relate to intermolecular forces, and the ones that we introduced at the beginning of this chapter were that Stronger intermolecular forces means we have a higher boiling point, a higher melting point, higher viscosity, higher surface tension, all those things. Here's two other ones that now we can know the relationship between intermolecular forces and these two. So stronger intermolecular forces implies a lower vapor pressure and a larger enthalpy of vaporization. And again, because if you have stronger intermolecular forces, it requires you to put more energy into the system to vaporize the molecules, to break those IMFs that are holding them in the liquid phase. Alright, so that's the relationship then between those. Alright, so any questions on that concept? Alright, the next thing I want to get into then is some more precise definitions of phase changes and how it relates then to these vapor pressures and enthalpies of vaporization. So the one that's especially important for us to understand this precise relationship is, what is the definition of boiling point? So we talked about in the beginning, we were sort of introducing phase changes. We said boiling point is the temperature at which a liquid converts into a gas. But now we have a more precise definition that's related to the vapor pressure of that liquid at a certain temperature. So the boiling point is the point at which, there's the temperature at which the vapor pressure is equal to the atmospheric pressure. Alright, so the boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. So once you get to that point, it is now favorable for the liquid molecules to become gas phase molecules, and you have the process of boiling, which is the complete conversion of the liquid into the gas. So just like any vaporization process, the enthalpy that's associated with boiling is still the enthalpy of vaporization. So boiling is no different than any other vaporization process. It's just that you've now reached a temperature where the vapor pressure is equal to the atmospheric pressure. And that's why you start to see bubbles form when you get to the boiling point. So we know that when we bubble water, or we boil water, you see bubbles coming out of the surface. And that's because you get this vapor pressure inside the liquid that's now higher than the atmospheric pressure. So the bubbles are able to form and then escape because they have a higher pressure than the atmosphere that they're surrounded by. Now, melting point, there's also a precise definition of melting point, although it's not as commonly invoked or used, but it's the temperature at which the vapor pressures of the solid and the liquid phases are equal. So we've talked exclusively about vapor pressures of liquids, but solids have vapor pressures as well. They tend to be much smaller than a typical liquid, but at some temperature, the vapor pressure of the solids and liquids are going to be equal to each other, and that's the temperature at which the substance melts or freezes if you're going the opposite direction. Alright, that's kind of a weird way to think about melting, but that's really the precise definition, and that's the temperature at which the melting point would be observed, is that temperature when you have vapor pressures of solid and liquid phases being equal to each other. And then melting, the process of melting, which is going from solid to liquid, or freezing, which is going from liquid to solid, those also have a vapor associated with, or sorry, an enthalpy associated with them. So we call that enthalpy of fusion, and this is specifically the enthalpy required to melt a substance. I'm not sure why melting is often called fusion, but it is. And this is the process again for melting. If you want to talk about the enthalpy change for freezing, which is going from liquid to solid, it will just be the negative of this. So just like boiling and condensation are opposite of each other's, fusion or melting and freezing are opposites of each other's, meaning the enthalpy changes are opposite as well. So that's the other phase change that we haven't talked so much about, which is melting. We're not going to do as much quantitative stuff with melting like we do with vapor pressure, but still there's some definitions that are important. And then the other thing that is important is the precise definition that we call normal melting or normal boiling point. And this is the situation when the surrounding surrounding pressure is 1 atmosphere. So as I said, in general, the boiling point is the temperature at which the vapor pressure is equal to whatever the atmospheric pressure is. And when we measure that temperature at exactly 1 atmosphere of pressure, we call that the normal boiling point. Or if you do the same thing for melting, it's called the normal melting point. So that means for the normal boiling point anyway, that occurs when the vapor pressure of the liquid is exactly equal to 1 atmosphere. So if we want to measure the normal boiling point of something, we do that in a pressure of 1 atmosphere. And once that vapor pressure of the liquid equals exactly 1 atmosphere, then you'll observe boiling. So the boiling point that you all know of for water, which is 100 degrees Celsius, that's the normal boiling point of water, which tells you then that the vapor pressure of water at 100 degrees Celsius is exactly 1 atmosphere. And that's why we call it the normal boiling point. It's when that vapor pressure is equal to the normal atmospheric pressure. All right, so those are some important definitions related to phase changes that we haven't seen yet. So now we can do one more calculation involving that same equation that we learned for vapor pressure and temperature. All right, so we're going to do it for water, or I guess not water, just a generic liquid. So a liquid has a vaporization enthalpy of 35.5 kilojoules per mole and a normal boiling point of 122 degrees Celsius. What is this boiling point at the top of Pike's Peak where the barometric pressure is 457 millimeters of mercury? All right, so what we've done here is we're trying to ask, if we go to a higher elevation where the atmospheric pressure is lower, what's the new boiling point going to be? Okay, so we know that for this liquid, the normal boiling point is 122, which means that at 122 degrees Celsius, the pressure is equal to 1 atmosphere. The vapor pressure is equal to 1 atmosphere. And so if we call that T1, 122 degrees Celsius, at 122 degrees Celsius, the vapor pressure of this liquid is exactly 1 atmosphere. That's why the normal boiling point is exactly 122 degrees Celsius. So again, thinking back to this equation here, we weren't directly told what T1 and P1 are, but we know that if the normal boiling point is 122 Celsius, the vapor pressure at that temperature is exactly 1 atmosphere, or 760 torr. All right, so then we can solve this equation for what the new boiling point is, which would be T2. So if we start putting numbers in, the ratio of the two pressures, P1 we're calling 760 torr, which is the normal atmospheric pressure. The pressure at the top of Pike's Peak is 457 millimeters of mercury, which is equivalent to torr. And that's equal then to, again, delta H of vaporization over R. We have to convert delta H of vaporization into joules per mole, so we multiply that by 1,000. Divided by R, which is the universal gas constant in joules per k-mole. And then we're multiplying by this difference of the inverse temperatures. So T2 is our unknown. It's what is the new temperature at which the vapor pressure is equal to 457 torr. And then the initial temperature is 122 degrees Celsius, which is 395 Kelvin. All right, so what we're asking then is at what temperature T2 will the vapor pressure be equal to 457 torr, and then at that temperature the liquid will boil at the top of this mountain where the vapor pressure is much lower. Okay? So we just work this out numerically. The left side of the equation is just a natural log of a ratio, so we can just put that down as 0.0586. And then that's equal to, if we distribute this out, I'm just writing out some of the algebra so you can follow it in case you have trouble. If we distribute this side of the equation, we get 4,269.9 over T2 minus 10.81. And then we just do some algebra to solve for T2. So in this case, we don't have to do as much with exponents because we already have two numbers under the natural log. And what we get is 377 Kelvin. which means that the new boiling point at the top of this mountain is 104 degrees Celsius, if we convert that to Celsius. All right, so when you go to high elevation where the atmospheric pressure is lower, the boiling point of a liquid will also be lower. So I don't know if you ever noticed or if they even still do this anymore. If you look at like the package of some food that you have to boil, like let's say macaroni and cheese or something, it'll tell you, boil it for 10 minutes, but if you're at, high elevation, boil it for 15 minutes instead, or something like that. They'll tell you to boil it for a longer period of time, and that's because when you're at higher elevation, water boils at a lower temperature. If you're cooking something at a lower temperature, you have to cook it for a longer period of time to get it fully cooked. So that's why that sort of happens, and when you go, and you can then use this equation to compare boiling points at different pressures, recognizing that the boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. So if you know the two atmospheric pressures that you're interested in, the temperatures that correspond to those vapor pressures will be the boiling points of those substances at those two different temperatures. Okay, any questions on that? All right, so that takes us to the end of vapor pressure. The last thing we're going to talk about today, just a few slides on this, is what's called heating curves. And so this is basically putting a lot of things together that we already know. So we're going to take a substance, we're going to start with it at some temperature with some, in some phase, whether it be solid, liquid, or gas, and then we're going to either heat or cool that substance to some other temperature, and we're going to determine the amount of heat that has to go into that or comes out of that when that process occurs. So let's first talk about what happens if we take a sample of ice and we just heat it at a constant rate. So on the left axis here, I'm showing the temperature in degrees Celsius, and then on the bottom is basically heat added. So as we just add more heat to the system, what happens here? So let's say we start with our ice initially at minus 20 degrees Celsius, and we heat it up at a constant rate. So at what temperature is it still going to be ice? Up until what temperature? Okay, so we know that the melting point of water is 0. Okay, good. So as we heat this up to 0 degrees Celsius, we're going to still be just ice. And it's going to heat up, the temperature is going to increase as we put heat into it. We know the equation for that, which is mc delta T. So as we put heat into our ice, its temperature is going to increase, but it's going to stay solid until it gets to 0 degrees Celsius when it's still ice. Once it gets to 0 degrees Celsius, it's going to melt. Okay? And at that temperature, as we have to put more heat in to convert the solid ice into liquid water, as we call it. And so there's going to be, the temperature is going to remain constant. So anytime you have a phase change, the temperature remains constant during the phase change because you're putting heat into the substance to convert it from solid to liquid, but you're not actually raising the temperature of it. All of the heat is going into the phase change process. So at 0 degrees Celsius, you have a mixture of ice and water that you have to put heat into until you've converted all of it into liquid water. Then once we convert it to liquid water, we can heat it some more. And as we've already seen many times in Chapter 8, when you heat up liquid water, the temperature is going to increase by that same equation, mc delta T. So once we get to water, we're going to increase the temperature again as we heat it up. And at what temperature does the water cease to exist? So up until 100 degrees Celsius, we're going to heat it up. It's just pure water at this temperature range, between 0 and 100. The liquid water is the only thing that exists. And up until that temperature, you're going to just increase the temperature as you put more heat into it. All right, and then if we go to 100 degrees Celsius, we start boiling the water to make gas phase water, which we sometimes call steam. So once again, as we put heat into this, we have to put heat in to change the phase from liquid to gas. So at this temperature, we have a mixture of water and steam, and the temperature remains constant during the phase change. So the temperature will not change as we convert liquid water into gas phase water or steam. And then once we get up to a high enough temperature, we've converted all, or not a high enough temperature, but once we've added enough heat to the system at 100 degrees Celsius, we've converted all of the liquid into steam, and then we start heating up the steam to a higher temperature beyond that. So at this temperature range above 100, so if we divide up our graph, we have these sort of segments here. So as we put in the heat to the system, we start with ice. We heat up the ice to 0 degrees Celsius. We convert the solid ice into liquid water. Then we heat up the water up to 100 degrees Celsius. Then we change the phase of the water from liquid to gas, water going to steam. And then once we have gas phase water, we can continue to heat that up as we add more heat to the system beyond 100 degrees Celsius. Now what I tried to show in here, although it's certainly not qualitatively or quantitatively replicative of the real situation, is that each of these segments is going to require a different amount of heat. It's not that you're going to put equal amounts of heat into each of these segments. And the amount of heat that's required for each of these segments here we can calculate using a lot of the principles that we already know. So let's then see how this works. Alright, so if we go and do this quantitatively now, let's say we have a 5-gram sample of ice at minus 20 degrees Celsius. So again, we're starting below 0 degrees. The temperature below that is where water exists as ice. And this is heated until it reaches the gas phase, and the final temperature is 140 degrees Celsius. So as we go from minus 20 to 140, we're going to go through 2 phase changes. We're going to melt the ice, and then eventually we're going to boil the water. And also we're adding a lot of heat to change the temperature. We want to know how much heat is absorbed during this process. So the way we want to think about these sort of heating curve type scenarios is, let's break it down into the different phases that we have that we already talked about. So the first phase, phase 1 as I'll call it, we're going to warm the ice from the initial temperature of minus 20 degrees Celsius up until the point when the ice melts. Now, we should know that for water, it melts at 0 degrees, boils at 100. Those are the 2 phase change temperatures you should definitely know off the top of your head. So we're going to warm it from minus 20 to 0 degrees, during which time it's exclusively solid ice. And the heat during this process is going to be equal to mc delta T. The mass of ice that we have, the heat capacity of the ice, or the solid in this case. Let's write it as solid, be a little more general. In this case it is ice because it's water, but the mass of the solid that we have, heat capacity of the solid, times delta T. And as you notice in this problem, the heat capacity for solid, liquid, and gas phase water are all different from each other. So the specific heat capacity depends on the phase of matter. We've learned for liquid water that the heat capacity is 4.18 joules per gram degree Celsius. We've used that number many times in the last section of the course that we did. However, if we're talking about water that's in the solid phase or in the gas phase, the specific heat capacity would be a different value for that. It is dependent on the phase. So for solid water, the heat capacity is 2.09. So we're going to use that number, 2.09 joules per gram Kelvin or gram degree Celsius, however you prefer to think about it. Although I should put the mass in first, sorry. So the mass of the solid is 5 grams. We're doing 5 grams of ice here. The heat capacity of the solid is 2.09. And then delta T, we're going from minus 20 to 0, so we're increasing the temperature by 20 degrees Celsius. So when we multiply those out, we see that we have 209 joules of heat that are required. As we'll see, our final answer is going to end up being in kilojoules, even though I didn't specify that. So that will be equivalent to 0.209 kilojoules. All right, so that's how much heat it takes to heat 5 grams of ice from minus 20 up to 0. That's just mc delta T, the same heat equation we've been using. The second phase is going to be the amount of heat that's required to melt the ice. And this is something we haven't exactly talked about yet, but what we should be able to recognize is that we have all these vaporization enthalpies in kilojoules per mole, and then the fusion enthalpy also in kilojoules per mole. So remember, melting, when we melt a substance, the enthalpy that's associated with that is called the fusion enthalpy. If it requires 6.02 kilojoules to melt 1 mole of ice or 1 mole of water, how much kilojoules would it require to melt 5 grams? So what we do then is we take, to find the heat that's associated with melting a substance, we take the mass of the substance. Sorry, well, we can do it in mass, but in more conventionally, we're going to do it in the moles. The moles of water that we have times the enthalpy of fusion, in this case, for melting. So we take the number of moles of substance, we multiply it by the enthalpy of fusion, which is in kilojoules per mole, and that gives us then the amount of heat that's required to melt that amount of substance. So the moles that we have here, we have to figure out the moles of water that we're dealing with here. It's just a simple mass to mole calculation. We have 5 grams of water that we're starting with, and then the molar mass of water is 18.02. So we have 0.278 moles of water. So typically when you're doing this, you're going to use MC delta T to calculate the heat that's associated with raising the temperature during one of the phases. And then for the phase changes, you're going to need to use the moles of water. So you'll use both the mass and the moles in these different steps. So if we have 0.278 moles of water, and then the enthalpy of fusion, which is the amount of enthalpy change required to melt the substance, is 6.02 kilojoules per mole. That comes out to 1.67 kilojoules. Alright, so it requires 1.67 kilojoules to melt 5 grams of ice, which is equivalent to 0.278 moles. And then finally, the third phase is now that we've melted all of the ice, we're in liquid water at 0 degrees Celsius, and so we're going to warm that liquid water up to the boiling point. So initially our liquid is at 0 degrees Celsius once we melted all of it, and it's going to remain liquid up until we get to the boiling point, which is 100 degrees Celsius. So the heat associated with this step is going to be, again, the mass of water that we have, MC delta T. I'll write that out explicitly. So we're going to take the mass of substance times the heat capacity now of the liquid, because in this temperature range the water exists as liquid water between the melting and the boiling points, times the delta T for this segment. So we have 5 grams still, we're not changing the amount of substance we have. The heat capacity of liquid water is the one that we're very familiar with, 4.18. And then the temperature change over this range is 100 degrees Celsius. We're going from 0 to 100. So for warming this in this range, we get 2090 joules, which is 2.09 kilojoules. So that's the amount of heat required to warm the substance. And then the fourth phase, we now have to boil this. So we're at the boiling point of water. We're going to take it into the gas phase. So phase 4, as I'm numbering them, is going to be to boil the liquid, boil the water. And again, the heat for this process is going to be the moles of substance that we have times the phase change enthalpy, which for boiling is this vaporization one here, 40.7. So when we boil the substance, the amount of heat that's required to boil it is the enthalpy of vaporization multiplied by the moles of substance that we have. So as we determined before, we have 0.278 moles of water. And then the vaporization enthalpy is given as 40.7 kilojoules per mole. So that means it requires 11.3 kilojoules to boil this much water. Okay? So that's the amount of heat required to boil the water. And then finally, the last step, we're getting towards the end finally, is the last phase 5, is now that we've boiled all the liquid, we have water in the gas phase, which we call steam or water vapor. And then we're going to heat that water vapor from 100 degrees Celsius up until the final temperature, which we're telling you is 140. So the final temperature in this whole process is 140 degrees Celsius. So the last step is going to be taking the gas phase water, we've done all the phase changes now, and we're going to heat that up to 140 degrees. So the last step is going to be warming the steam that we have from the boiling temperature at which it first forms to the final temperature, which in this case is 140 degrees Celsius, as we're told in the problem. So in this stage, once again, Q is just equal to MC delta T, but this time we have to use the heat capacity of the gas phase, because we're in the gas phase now. So it's still 5 grams of substance. The heat capacity for gas water is exactly 2 joules per gram degree Celsius. So again, different heat capacities for each phase of matter. And then delta T in this range are going from 100 to 140, so that's 40 degrees Celsius difference. And so this comes out to 400 joules, which is 0.4 kilojoules. And then finally that we have all of these individual heat values. The total amount of heat that was required to do all of this is just the sum of all 5 of these. So we calculated the amount of heat that was necessary to warm the ice to 0 degrees Celsius. then the amount of heat that was required to melt the ice, the amount of heat that was required to warm the liquid from 0 to 100, the amount of heat that was required to boil the liquid, and then finally the amount of heat that's required to warm up the steam to the final temperature. And the heat that's totally, the full amount of heat that's involved in this process is just the sum of all of these. So 0.209 kilojoules, which is the amount we got for the first one. 1.67 kilojoules is the second phase. 2.09, 11.3, and then 0.4 for the last one. So when we add all these together, we get 15.7 kilojoules, the total amount of heat that's required to do this whole process. All right, so that takes us all of the possible steps. We won't typically give you problems that involve all 5 of these steps, but if you wanted to go all the way from a solid into the gas phase over a temperature range, this is how you would do it. And you might notice that most of the heat that was required for this process, 11 out of the 15.7 kilojoules, is the amount of heat that's required to boil the substance. And that's a pretty typical situation, because to boil a substance, we have to break all of the intermolecular forces in that substance, which in case of water especially are very strong hydrogen bonds. So it requires a lot of energy to boil a substance, so most of this 15.7 kilojoules is just the amount that's required to boil it. All right, any questions on that one? Yep. So these enthalpy changes associated with... All right, so remember we talked about in Chapter 7 thermochemical equations? So this enthalpy value for vaporization and fusion is the amount of heat that's required to either vaporize or melt 1 mole of that substance. If we want to figure out the amount of heat that's required to vaporize some other amount of that substance, we take the number of moles of that substance and multiply it by the enthalpy of vaporization, which is kilojoules per mole. So if you look at the units here, we have 0.278 moles of water multiplied by the enthalpy of fusion, which is 6.02 kilojoules per mole. The moles cancel out, and that tells us how much heat in kilojoules is required to melt that much substance. So it's just like any sort of thermochemistry type problem. The amount of substance, if you know the amount of enthalpy change per mole, if you multiply that by the amount of substance that you actually have, that will give you the enthalpy change for that process. Any other questions? Yeah. Yes. It could be degrees Celsius or Kelvin. Remember that for heat capacities, we were talking about delta T. Those are interchangeable. Anything else? Oh, sorry, back there.
Why does specifically ice become specifically as much as water?
So, let's see. Best way to answer this one. So the reason is that the thermal conductivity of the two substances is different. So and I think the reason specifically is that in ice you have a sort of a rigid hydrogen bonding arrangement between all the molecules, and ice is actually less dense than water. In water, you actually have a greater ability to hydrogen bond because the water can adapt more orientations and surround itself. So basically, to increase the thermal motion or increase the kinetic energy of the liquid water molecules, you have to break more intermolecular forces of attraction. So in any phase of matter, the intermolecular forces are going to be different between one phase and the other. Heating up a substance requires you to give it thermal energy that makes those molecules move faster in that phase. And so depending on the exact arrangement of intermolecular forces, you're going to have different values. Now, in terms of predicting the difference between the different phases, there is no regular pattern there. So we saw that in water, liquid water has a higher specific heat capacity than either the solid or the gas. That's not necessarily a general outcome. So in some substances, the liquid could be lower than the solid, and so all these different possibilities occur, but it depends on the precise structures and the types of forces that are involved in propagating thermal motion through that substance. So it's a pretty complicated thing to think about it in general. Good question, though. Anything else? All right, let's just do one more example of this type of problem, a little bit less involved this time. So let's say we have 0.33 moles of gaseous ethanol at 300 degrees Celsius, and we want to, and the pressure is 1 atmosphere, and we want to cool this to liquid ethanol at 25 degrees Celsius. All right, so again, we're cooling down a gas to a liquid in this case. Now, if we look at the we're not told what all the different parameters are. We don't need all of them here, but we see that the boiling point for ethanol is 78.5 degrees Celsius. So initially when we're at 300 degrees Celsius, we're going to be in the gas phase. We're above the boiling point. We're going to cool it down to 25 degrees Celsius, which is below the boiling point. So we're going to go again from gas to liquid, but that's going to be the only phase change we have in this situation. So again, it's helpful to break this down into different phases. And so the first one here, we have vapor. We're going to cool that down from the initial temperature. And we're going to cool the vapor down up until the boiling point. Because once we get to the boiling point, here we're going in the opposite direction. We're going from vapor to liquid. Once we get to the boiling point, the vapor is going to convert into liquid. So you're going to cool it from 300 degrees Celsius to whatever the boiling point is, which we're not talking about water anymore. So for this substance, the boiling point is 78.5 degrees Celsius. So that's going to be the first phase, is cooling the vapor down up until the temperature at which it will start to condense, which is at the boiling point. So in this phase, heat again is just given by mc delta T, where we need the heat capacity of the vapor in this case, or the gas phase heat capacity. So we have 0.333 moles of ethanol. So we need to find the mass of that. So the mass of ethanol is going to be 0.333 moles. So we do need moles and mass to be able to do this, as I said. So did I tell you I didn't tell you the formula or the, this is a bad problem. Anyway, you wouldn't have to know what ethanol is, but it's going to be C2H6O is the formula, and then we multiply by the molar mass to get the grams of ethanol, which is 46.1. So I should have given you the chemical formula. I apologize for that. But if you have the chemical formula and or the molar mass, you'd be able to convert grams into moles, because we do need both quantities here for this problem. Alright, so that's going to be 15.3 grams, is that 1/3 of a mole. So for the first phase, we need the mass because we're using mc delta T. So we have 15.3 grams of ethanol. The heat capacity for the gas phase is this one here, 1.43. So again, we see that liquids and gases tend to have different heat capacities. Still the same story here, the gas being lower than the liquid. And then the delta T for this step is going to be, we're going from 300 to 78.5. Now keep in mind we're going in the opposite direction. So our final temperature is 78.5. Our initial temperature is 300. So in this case, our heat is going to come out to be a negative number, 300 Kelvin, which is 300 degrees Celsius, sorry. Confusing myself here. So all the temperatures in Celsius, we don't have to convert anything. So that's the temperature change, though, final minus initial. We're cooling the substance down, so it's going to be a negative delta T. And what we get then is minus 4,846 joules, which is minus 4.846 kilojoules. All right, so this time we're cooling the substance down, so Q is going to be negative. Heat is released from the system because we're cooling it down to a lower temperature. And then in the second phase, we're going to take the gas phase ethanol and we're going to condense it into a liquid. So the second phase, now that we're at the boiling point, is we're going to condense from gas to liquid. Again, in this case, we're lowering the temperature during the process, so we're going to do condensation. And so the heat for this is going to be the moles of ethanol times the enthalpy of vaporization, which is the enthalpy change associated with it. However, keep in mind that we're doing, in this case, we're not doing vaporization, we're doing condensation. So really what it's going to be is the enthalpy of condensation, which is the negative of the enthalpy of vaporization. So because we're going in the opposite direction for this phase change, we have to multiply by negative enthalpy of vaporization. So we have 0.333 moles, and we're going to multiply that by negative 40.5 kilojoules per mole. So So we get minus 13.49 kilojoules. Again, a negative enthalpy change because we're going in the opposite direction. We're going from from gas to liquid. And when we do that, it releases heat to the system. All right, so imagine if you let water vapor, if you let steam condense on your hand, which is not a very smart decision, your hand's going to get really hot. And that's because as the water condenses from gas to liquid, it's transferring its heat to you. So we're losing heat from the system, so we have a negative enthalpy change anytime we're going from gas to liquid or from liquid to solid. And then finally, the last phase, in this case, we're in the liquid phase now. We're going to cool from the boiling point, which is 78.5 degrees Celsius, to the final temperature, which we're told is room temperature 25 Celsius. That's where we stop. We don't have any more phase changes to worry about. And so again, for this phase, we're going to use Q is equal to MC delta T. This time we need the heat capacity of the liquid phase, because we're talking about the liquid phase now. So we said the mass is 15.3 grams. Heat capacity for liquid ethanol is 2.45. And then delta T is 78.5 down to 25, so it's going to, again, be final minus initial, negative delta T. So we get minus 2005 joules, which is equal to minus 2.005 kilojoules. And then finally, the total heat for this process, with the correct sign attached to it, is the amount of heat required to cool the vapor, which is minus 4.846. Sorry, let me rewrite that. Plus the amount of heat required for the second phase, which is also a negative number, minus 13.49 kilojoules was released when we condensed the liquid. And then for the last phase, we released minus 2.005 kilojoules as the liquid cooled down. And that should give us minus 20.3 kilojoules. All right, so we lose 20.3 kilojoules of heat when this vapor that we have, this vapor of ethanol, cools down, condenses, and then cools down further all the way to room temperature. All right, so that's how much heat would then give up to its surroundings. So these heating curves, you can have either positive or negative heat depending on if you're adding heat to the system to raise the temperature and induce phase changes from solid to liquid to gas, or you can have negative Q terms if you're cooling the system down, which is going to lower the temperature and then induce phase changes from gas to liquid to solid. So that can work in both ways. All right, questions on this topic? I think that's the last thing that I had. No, sorry, superheating and supercooling is the last thing I have. I promised I'd let you out early, and I'm not going to probably keep that promise by very many minutes, but it'll be a little bit early. Okay, so anyway, supercooling and superheating, these are just a couple concepts to be aware of. So we said that normally when you cool a liquid to its freezing point, it's going to go from liquid to solid, but it is possible in some cases to have a liquid cooled below its freezing point and still remain as a liquid. So sometimes you can cool a liquid below the freezing point without changing it to a solid. So you could have water that's existing at minus 10 degrees Celsius. Normally you'd expect it to be ice at that temperature, but for some period of time it persists as a liquid even though it's below the phase change temperature. And why does this occur at all? Well, there's a couple of different reasons why, but really it's that in order for a liquid to freeze, in order for it to go from liquid to solid, the molecules need to organize themselves. So in the liquid phase, the molecules are all loosely tumbling around, they're all freely moving around each other. And then when you go into the solid phase, they have to organize themselves into a regular crystalline array, as we talked about for structures of solid materials. And so for that process to happen, sometimes it just requires some time for that to occur. It's not that there's any real reason why it would want to be a liquid at that temperature. It's just that it takes time for the molecules to organize and to crystallize. So it's just a sort of more of a kinetic process that you have to think about. So depending on the rate of cooling that you have, so especially if you cool the liquid down really fast, the liquid might not have enough time to organize into the solid phase. So it may not achieve the level of organization needed to actually freeze. All right, so as I said, sometimes it takes time for the molecules to come together and organize themselves into the correct structure to be able to form whatever solid crystalline phase exists, which for ice we know is hexagons of water molecules all hydrogen bonding to each other. All right, so that's why supercooling occurs, and then superheating is sort of the opposite. If we heat a liquid up, sometimes it's possible to heat the liquid above the boiling point without it actually starting to boil. And there's not really a real chemical explanation for this, but this can be caused by uneven heating. So if the heating of the liquid is uneven, meaning some parts of the liquid are hotter than others, there may not be enough high energy molecules to form a vapor bubble and escape. So in order to form these bubbles that escape the liquid, and when we have boiling occurring, you need to have a lot of these high energy molecules close to each other that sort of group together into one of these bubbles. And if there's not enough of them near each other at a given period of time, the liquid might not boil right away, even if it's at a higher temperature than its boiling point. Alright, so we don't want you to know too much about superheating and supercooling. They are important processes in some applications, but we just want you to know their definitions, a little bit about why they occur. So that's all the level of depth we're going to go into. So the last topic we'll cover on Wednesday before starting to review stuff for the final is going to be phase diagrams, which is the very end of it. So I'll see you guys then.